Hi guys. So in this video, we are going to solve the heat equation, partial differential equation. And then, we are going to solve it using two ways, the Fourier transform and the variable separation method, which is again just trying to use the ordinary differential equation after separating variables, right? And there are a few restrictions on variables, like the time variable should be greater than equal to 0, or the spatial x variable should be between minus infinity to infinity, right? And there are a few initial condition and boundary value conditions. Initial condition is that the u function at time equals to 0 with variable x is this f of x. And then, since there's f of x, we will not be able to get a particular solution. I mean, show an exact solution, but it will be in terms of f of x, right? And then also for the boundary condition, we are given that this u function at 0, t is 0 and at l, t is 0, and that will be helpful for us later on. So for now, let's go on solving this problem. Okay, now first of all, we will do using Fourier transform method because that's a little easier. Okay, so we have, I'm sorry. So we have this following partial differential equation. Partial u by partial t is equals to alpha square times partial square u by partial x square. Okay, so in Fourier transform method, what we are going to do is we are going to take Fourier transform of the entire PDE, right? But again, there are two variables, and Fourier transform is defined in terms of single variable. So we first need to define how we want to define it. Like define the Fourier transform, with respect to x, If we do that, basically over here our function is u, right? And u is a function of x comma t, right? Okay, so let's say if I take sorry, I'm used to the Laplace transform. Okay, so if I now take the, let's say, Fourier transform of u of x comma t, this will just be integral from minus infinity to infinity of u of x comma t and then e to the power minus I omega x dx. We are defining it with respect to x, right? So this is the definition of Fourier transform. And okay, notice that after we do the integral, this function will be in terms of omega and t, right? So our Fourier transform, let's say for a small u, the Fourier transform is capital U, will be a function of omega and t, right? Okay. So now let's take the Fourier transform of PD. Let's take Fourier transform with respect to x of PD. Fourier transform with respect to x of PD, right? So that will just be Fourier transform of partial u by partial t is equals to alpha square times Fourier transform of partial square u by partial x square. Okay. Now, since this Fourier transform is with respect to x, a good thing is since it's with respect to x, like for the partial by partial t, this will just be partial by partial t of the Fourier transform of u. Okay, so and Fourier transform of u is just capital U of omega comma t, right? Okay, so that's what happens. Like basically, you just take the Fourier transform of this u variable, this u small u, that becomes capital U, and now it becomes function of omega and t. And like the Fourier transform, if it's with respect to x, you can actually prove this thing like how, like from the main definition, right? This will just be I omega times the Fourier transform of small u, which is capital U, and its function of omega comma t, right? Okay, so basically, I omega times the Fourier transform of this function u x comma t. So the thing that happens is when you have it that like derivative, you get the integral of that function. We get the integral of this function over here along with I omega in front of it. So from here you can like possibly guess that, let's say if I want to take Fourier transform of partial square u by partial x square, and this Fourier transform with respect to x, then you will just have first of all I omega times the Fourier transform of partial u by partial x. And again, if you take it, I omega times I omega of the Fourier transform of this small u, that means negative omega square times the Fourier transform, which is the function of omega and t. So I guess we get the idea of how it's going on, right? So now let's use these two results, this one and this one, in our initial problem over here, right? So if we do that, we just get the partial of the Fourier transform of u, small u, which is capital U, which is function of u is now function of omega comma t because it's a Fourier transform, right? And this is alpha square times negative omega square times Fourier transform. And I don't, let me not write that u is a function of omega and t again and again because that makes it messy. You know that, right? Okay. So now we actually want to, okay, after taking the Fourier transform, uh, I can actually, it doesn't matter. Okay, fine. Now I can actually take the u in the other side, right? And then, yeah, now I can solve this. Now I can integrate this on the both side. And then I'm actually trying to solve for this u of omega comma t. Okay, so that's why I'm trying to solve for that. And this will, we actually know directly that this is a well-known integral for exponential, right? You will first get ln and you take it to other side. So yeah, we know that becomes a c and then e to the power minus alpha square omega square t, right? We know this thing. So okay, now over here, if you want to solve for c, notice that c actually need not be a function because over here c can still be a function of omega as well, right? Or do you think so? Yeah, yeah, that's the case actually. Now, okay, to solve for c, what we're gonna do is, since we know that this is a function of omega and t, now our like initial condition like was in terms of uh x and t, right? Our this was actually u of x comma 0 is f of x, right? Now, if we just take Fourier transform of both sides, Fourier transform of this initial condition, then you what you will get is this will just be a Fourier transform of u is capital U of omega comma time is just 0. And let's just define the Fourier transform f of x to be capital F of omega, right? This will be function of omega now because x is to omega after going through Fourier transform, right? Because there's omega over here in the integral. So yeah, let's just use this initial condition now. So that gives us yeah, substitute t as 0. So then this will be 0. Let me actually not write C1. That doesn't make sense. Okay. And now we know that it's just f of omega becomes c. So yeah, c basically f of omega. So we have Fourier transform of u to be f of omega times e to the power minus alpha square omega square t. Okay. So now we are gonna solve for u x comma t, right? So definitely the thing that we are going to do is take a Fourier inverse transform of both sides. Take Fourier inverse transform. Now, in like Laplace inverse transform, we actually not to need to know the formulas, but in this case, we don't really need to know that. Like, actually, it's easy for the Fourier inverse transform. We basically know that. Like, let's say if I want to find f of x from the f of omega, so that's just like 1 by 2 pi times integral from minus infinity to infinity of f of omega times e to the power I omega x dx, right? So that's how we get the Fourier inverse transform in this case. Let's say if I want to have this in terms of s, then I just need to change x by s. It's as easy as that. See? Similarly, let's say if I want to get u of x comma t from u omega t, I just do the same thing. 2 pi from minus infinity to infinity, a capital U of omega comma t to the power I omega x dx. So yeah, it's sorry, it's x is as easy as that. Hmm. So yeah, this is the thing that we're going to do. And over here, if we take Fourier inverse transform, we know that Fourier inverse transform of u omega comma t is just u of x comma t, right? Wait for the second, like for the right hand side, we actually need to do it. It will be 1 by 2 pi times integral from minus infinity to infinity of f of omega e to the power minus alpha square omega square t dt. Am I doing right? I hope I am. Yeah, I just hope that I am because because I have got sense that hmm. Just a second, just a second. Let me check my progress till now if it's going in the right direction or not. Because if I'm missing something right now, and then if I just go ahead, there could be a problem. So, yeah, there's actually a problem, I guess, because I did not introduce I omega x. Okay, yeah. I also I should along with this function, if I want to take it. Sorry. Okay, if I want to take its Fourier inverse transform, along with this function, I also need to introduce this variable, right? If I would introduce that, and then this will be e to the power I. And now I want to change this to x, so I omega x dx. So that's what it needs to be done, right? Okay. Now that's good. Now it's all good. You okay? Yeah. Okay. Now the thing is, because I wanted to take its Fourier inverse transform, so I need that function times this variable, right? And then all the things the same. So yeah, I forgot this. So I was trying to say. Now after this, we know that f of omega was just the Fourier transform of x. So basically, I will write that. And since x is already used, now in this case, I will just use minus infinity to infinity. Let's say f was a function of s, and then e to the power minus I omega s ds. This basically gives the Fourier transform of the function f, right? And that's what we need. Minus alpha square omega square t I omega x dx. Yeah, now everything is basically going to be in the now if I evaluate this integral, now this is actually our solution, because we just need to evaluate this integral to get the solution right in terms of x and t, and that's it. But let us just simplify it a little bit more. So u of x comma t, what you can do is you can actually like, okay, first of all, let me just like multiply and simplify a little bit. Minus infinity infinity minus infinity infinity f of s e to the power minus I omega s e to the power minus alpha square omega square t e to the power I omega x and then dx. Now the thing is, we can actually simplify it if we say, oh, I forgot ds over here. If we simplify the order of s and x, like this order of integral, we can actually simplify, because f of x, f of s now goes outside, right? What I mean by that is, now actually I can keep f of s as constant if the second integration is in terms of x, right? I omega s minus alpha square omega square t plus I omega x, now dx ds. Okay. Now this can actually be solved using like Gaussian integrals a little bit, not a lot, but a little bit. So let's try that. So f of s, now from minus infinity to infinity, if I take minus alpha square t common, I will just have omega square, right? And then I will have, okay, so basically I will now have is by alpha square t minus ix by alpha square t. So that's what I have, right? Yeah. And then there's dx. Now I will just try to complete the square. It looks terrible, but it's not that terrible actually. Even though it looks like that, you can actually do it. U of x comma t is 1 by 2 pi minus infinity to infinity f of s, and then from minus infinity to infinity again, e to the power minus alpha square t. So this is omega square plus 2 times, oh, I forgot to write omega over here. There's omega. 2 times omega times, now this is just is minus ix by alpha square t, also, or 2 over here. That makes it a square plus 2ab. Now I need a b square. So is minus ix by 2 alpha squared. This is b square, right? I also need to subtract it because I introduced it myself. So minus is minus ix by 2 alpha square t whole square. This looks long, but now it's going to simplify. I promise you that it's not going to be terrible as it looks now. So u of x comma t is 1 by 2 pi minus infinity infinity f of s minus infinity infinity. While doing maths, you do need some patience, right? Because it takes time for things to simplify. Omega times is minus ix by 2 alpha square t square, right? Oh, guys, I'm sorry for something. I think I should be sorry for something. Because this first integral should actually be in terms of omega, right? Only then, like, because only then if it's terms of omega, then I can get it in terms of x and t. Man, damn it! This is in terms of omega. I'm sorry. This is such a huge blunder. Omega, 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 omega. Yeah, no, it's okay. Yeah, no, that's fine. And then we'll have a minus over here. Actually, this minus over here, there's a minus sign, but also there's I square from inside. So that way square makes it plus, and then s minus x by 2 alpha square t square, right? And then d omega ds. Okay, now we really have a lot, only a slightly few more steps to simplify. Minus infinity infinity f of f minus infinity infinity e to the power minus alpha square t. Now this is just first of all I can write it as omega plus is minus ix by 2 alpha square t square time. This is now just I can write uh, s minus x as x minus s square for some nonsense reasons. There's no reason for that though. And 4 times this is just alpha square t, right? Because there's a square, so that cancels out. Okay. And now, yeah, now this is just d omega ds. Now notice that this thing over here is actually a constant, right? For the omega integral, for the integral with respect to omega. So let me take that out. Minus infinity to infinity, f of s, e to the power minus of x minus s square by 4 alpha square t. Now, the first integral is just like Gaussian integral, right? And if the limits is from minus infinity to infinity, and if integral is in terms of omega, it doesn't really matter. Omega plus some constant, that doesn't really matter. That's just the same as being omega square only. So yeah, this is just like e to the power minus alpha square t omega square d omega. So this is a constant, doesn't really matter. So we know that if it's like e to the power minus a omega square d omega, that's just root pi by a, right? So yeah, that's the same thing. It should just be root pi by a, where a is just alpha square t, right? So yeah, that simplifies a lot. And then this is in terms of ds now. So u of x comma t is 1 by 2 pi, and if that comes out, that's just root pi by alpha square t from minus infinity to infinity f of s e to the power minus x minus s square by 4 alpha square t ds. Now I can simplify this as u of x comma t is just square root of, that's just 1 by 4 pi alpha square t, right? 4, so, and then from minus infinity to infinity, f of s e to the power minus x minus s square by 4 alpha square t ds. And that's finally our solution. Okay, guys? Yeah, and I think for this video, we'll just solve it using the Fourier transform method, because I think the video is getting long, and also my charge is just 6% now. So yeah, we will do with the next method in the next video. So that was the solution, guys. It doesn't really look that pretty, but yeah, this is it. Actually, like if you go with the ordinary, like the variable separation, the solution would be more comprehensible and like that would be slightly different, and that actually looks beautiful. But this one, like that solution is in terms of the infinite series, but this is in terms of an integral. It's definitely they are different. And also, I didn't really use the boundary value conditions, which you can now use to solve for these constants, like these constants are as alpha and these things, right? You can use definitely. But yeah, this is the solution, and like we aren't going to do in okay, we aren't going to solve for like alpha because we don't really know the function f over here. If we had known that, we could have made some progress, right? So for this video, I think it's that's it. And then I hope you enjoyed the video. And yeah, see you in the next video where we solve it using the variable separation method. That's it.